everyone. First of all, I want to thank all of you for joining this session. My name is Tushka Dermenjieva, and I'm the technology manager of our Java and integration team at Scalefocus. Before we start, I want to share more details about the Tech Savvy Talks initiative hosted by Scalefocus. So today's event is the first of many we plan to organize. We're going to host events every 2 weeks where different topics will be presented by different speakers from Scalefocus who are specialized in different fields. So stay tuned. And as you know, today, Vasil, who is one of our most experienced engineer from the Java team, will present you very interesting topic related to microservices decomposition patterns, where he will share his experience, good practices, and of course, challenging he learned on the way. Before I pass the ball to Vasco, I want to mention some housekeeping details. Keep in mind that the session will be recorded. So there will be also interactive Q&A session at the end. And for the session, you can subscribe to Slido. You are seeing on the screen. And you can add your questions. Vasco, the floor is yours.
Hello to everyone from me. I am glad I have the opportunity to be a presenter in the first occurrence of this amazing event series. I'm going to start with a few words about me. My name is Vasil Kostudinov, and I've been in the software industry for a little bit more than 6 years so far. And some of the major projects that I've worked on are from the fintech, e-commerce, and health insurance domain. Most of my contribution to those projects was on the back end, and the primary language that I've used the most is Java. So Java is the language that I'm most familiar with. Besides that, I love my job. In my spare time, I like to travel, visit new places, and try different foods, because who doesn't like to eat? And also, I have a LinkedIn profile where you can contact me if needed. So that's pretty much about me. Moving on to the topic for today's presentation, which is monolith decomposition patterns, and more specifically, decomposing a monolith and moving towards a microservice architecture. And the reason I picked this topic is because microservices became a trend for the past few years, and they started being adopted by a lot of teams and in a lot of projects, and a lot of people try to do them. Some succeed, for others think don't end up so well, and they even start wondering why they even went that path, because moving to such kind of architecture has some serious challenges and risk that you have to face. Also, there's something that we are doing in our current project, and I just thought it's an interesting topic overall. And beside that, microservices looks great in your CV. They also have some other benefits, which we will be discussing during the presentation. So the agenda that we have today is what is monolith, and where we will be discussing some of the pros and cons of the monolithic architecture. We are going to do the same thing for the microservice architecture, because the first thing before moving to microservices is to decide whether you really need them or not, and to the challenges that you're going to face, what the benefit that you will gain. Under defining boundaries, we will be looking at some rules and guidelines that we can use in order to design and model our microservices in order to get the most out of them. After that, we'll go over some patterns that we can use to decompose those pieces from our monolith and integrate them with the current monolithic system in a safe manner, and who does not like patterns after all. And at last, we'll be looking at different approaches that we can use when our microservice needs to access some data. So what's the monolith? From an architecture point of view, what we have is all our code, which resides in a single repository or a single code base, and all that code gets compiled and packaged as a single deployment unit. And that deployment unit runs within a single process. From the database perspective, we have one database where all the data is being persisted, and it's directly accessed by each part of the monolith. What are some of the pros of the monolithic architecture? Well, it's simple to develop since the monolithic approach is a standard way for building an application, and almost every team has the right knowledge and expertise to develop such kind of applications. It's also easier to debug and test, as our code is at one place, and tracing the execution flow is easier as well as end-to-end testing. It might perform better because the communication between modules is local, since the whole application runs within a single process, and there is no network latency, and the user experience might be better. It's also easier to deploy since we have one artifact that we need to deploy and don't have to worry about multiple deployments. It has less cross-cutting concerns because functionalities like exception handling, caching, and logging are easier to manage when they relate to a single application. Data access is also easier because all the data resides in a single database, so each module within the monolith has access to it, which makes some database operations like joins, for example, a lot much easier. Now we'll be looking some of the cons, and first thing we have so large code base. And since we have a single code base, the tendency along with the time is for that code base to grow. And as with all large things, they're hard to manage. It is difficult to understand, again, based on the large code base, such applications could be hard to understand. For example, if you have to onboard a new joiner, for example, that code could be hard to grasp at first glance. It's slow, it has slow compile and start time, and people who have worked on such projects know the pain of compiling and running them for tens of minutes when you have to develop and run them locally. There is high coupling between modules because all the modules are statically linked and communicate on a code level, and change in a given module can have impact on other parts of the system. They're hard to scale in the sense that we have a single process that we have to scale, and most of the times not all modules within the monolith are equally loaded. The deployment become less frequent because when an application has grown to a certain point, the release cycles slow down because all the changes that are going into the release have to be carefully coordinated between all the teams. Now, let's dive into the scaling part and what I meant by hard to scale. Here we have an image which shows our monolith with all the modules within. And let's say that our business has grown and more users start to use our system, and they are logging, registering, authenticating, and so on. Or in other words, actions which the authentication module has to perform as shown in our image. Now, the most useful thing that we can do is to scale our system in order to handle the increased loads. And now the things start looking more like this. And as we can see, what we did is that we scaled the whole monolith up to 2 instances and distributed the user load between them. But what we also did is we scaled modules that don't actually need scaling just because they belong to the same process. And that's not very optimal because in this way, we've kind of wasted system resources to support other modules that we don't really need because they're not the ones being overloaded. Now back to the less frequent deploys. On this image, we can see a graphic that represents the amount of code going in each release as our deployments become less frequent. And less frequent releases lead to more code being released, which itself leads to a greater risk of regression, which is something we would really want to avoid, right? Now, before we move on to how microservices address those problems, let's talk about what a microservice architecture actually is. And that's a type of architecture where our system is composed of many independently deployable small services, where each service runs within its own process. And all those services communicate with each other over the network by using a well-defined interface and protocols like HTTP and REST, which enables them to be loosely coupled. And what are some of the pros of the microservices? Well, they allow for high team autonomy because each team can focus on his own set of microservices related to a given business domain, instead to be responsible for functionality which is split across the same code base where other teams operate as well. It allows them to be independently deployable. And since all microservices work in isolation and within their own process, each team can deploy independently without interfering other teams. And the ability to make a change to a piece of functionality in the scope of a given service and redeploy that service and to release that functionality without having to change and redeploy other parts of the system is the one of the most important benefits. We have more granular scaling, and as we can scale a single piece of our application, as opposite to what we had in the monoliths. We have fast release cycles, again, because the ability for each team to scope their changes and release independently, the release cycles become more frequent. Now, how microservices would address that the problem that we had with the user vote in our previous example. As shown on this image, if we have our authentication module extracted to its own service and own process, what we achieve is more granular scaling, which enables us to scale only that module that is actually being overloaded without spending extra system resources to support other modules coupled in the same process as we had in the monolith case. Moving on to the more frequent deploys. Now this is how the graphic would look like as opposite to the monolith. Teams can release independently, which allows them to release less code more frequently, which leads to a low risk of regression, which is great. But all that benefits comes with a price, of course. So let's go over some of the microservices cons. They can perform poorly since all the modules run within their own process and the communication between them is on a network level. So there is a latency which we can't avoid. Debugging and logging is also a bit harder because having such type of architecture, every request is being processed from multiple services, and each service has its own logs, which makes troubleshooting the system problems harder. Database transactions could also be an issue because transactions now span across different services and databases, and achieving consistency, or in other words, distributed transactions, could be a real challenge even for highly skilled developers. And yeah, it's a distributed system, and when different parts of the system communicate over the network, there is always a chance for something to go wrong. For example, if some microservice go down or we lose network connection, overall, making such systems resilient and fault tolerant is pretty hard. Now, since we're aware of the pros and cons of both architectures, and we still decided that we need and want microservices, let's go over some rules and tips which can help us design and model them properly. Microservices should be modeled around business domain and business functionality, but not based on some technical abstraction. They should group and encapsulate business logic and capabilities, and changes to a given functionality should happen inside the scope of a given microservice. They should also have single responsibility, similar to the solid principles that we have in an object-oriented design. A microservice should also do one thing and do it well. We also should avoid dependencies, which will require us to deploy multiple services at once. And the splitting of functionality between multiple services makes them dependent on each other. Maybe that's a sign that this functionality should belong to a single service. They should be loosely coupled and be able to evolve independently. And by using a network communication and well-defined application interface, we can achieve loose coupling between different modules, as opposite to the monolith, where modules are coupled on a code level, and this would allow our services to evolve independently. So by using these tips we just went over, we can guarantee that our microservice design will be correct in order to get the most out of this type of architecture. Now, if we don't want our architecture to look something like this and have messy dependencies which are hard to maintain, we need some patterns to make our decomposition and transition to microservices more safe and less painful. We'll go over two patterns which serve different use cases, the Strangler Fig and the branch by abstraction pattern. The first pattern we will go over is the Strangler Fig, named after a plant which wraps around a tree. It does a similar thing to our architecture, but in a different way. And it's a simple and useful pattern, and it's also very easy to implement. And how it works is that once we have identified and extracted the functionality we want, and by extracting, I mean like rewriting it or duplicating it to a new place instead of moving it out of the monolith, because in this way, we can make sure that we will have the option to switch back to the legacy implementation in case of something goes wrong with our new one. Then we will just redirect the calls from our monolithic system to our new microservice. But in order to do so, we need something which will do those redirects for us. For this purpose, what we can use is an HTTP proxy, which we are going to place in front of our monolith, which will just pass all the calls to the monolith as is. But what this allows us is at a later point when we have our microservice released and deployed in production environment to change some proxy configurations and reroute the traffic for that given functionality to our new microservice. Later, if we see that something is wrong and our new module does not work as expected or does not perform as expected, what we can do is, again, just change some proxy configurations and reroute that authorization traffic back to the monolith without having to redeploy our application again. Now that pattern works well, but it doesn't solve all our problems. For example, if we have a use case like this one, and let's say we want to send emails to every customer upon registration. In this case, what we can't intercept the calls to the email module, since those calls are internal and happen inside our monolithic application. And such actions are triggered by another module, but not as a result of a direct user interaction. To solve such problems, we can make use of the branch by abstraction patterns, and the steps for implementing this pattern is to define a point of abstraction, implement the new functionality, and switch from the old to the new implementation. At the following diagram, we have our authentication module in orange at the top, which calls the email service implementation. As a point of abstraction, what we can use is define an interface for already existing legacy email service implementation in the context of object-oriented programming, and define a new implementation for that same interface, which will make REST calls to our newly extracted microservice. For the logic whether to use the new implementation or the old implementation of that interface, often is used something called a feature flag. And the idea of that feature flag is to allow us to switch between those two implementations at runtime. As an example, this could be a REST call to another service which returns a true or false flag, whether the new implementation is on or off, or for example, a JMX feature for those who are familiar with the Java stack. But the basic idea is to have the option to control this flag without having to make code changes and without having to redeploy our application. This way, if something goes wrong during the production, we can quickly switch back to the legacy flow without making code changes. And once we have run the new implementation for some time, and we've decided that it works well and fulfills our needs, we can clean up the old implementation and the corresponding feature flags and just keep the new one. So now, what about the data? Most of the times, our microservices will need some data in order to perform their actions. And the question is how to get that data. So here we basically have two options: to use shared database and database per microservice. And here is how the shared database pattern looks like. Our new microservice could access the monolithic database directly, which is a quick and easy solution, but it's not optimal in the long run, since this approach introduces dependencies as changes to the database schema have to be reflected in both applications, and in a sense we lose that independent deployment that we talked about earlier as a main benefit of the microservices. And although it's not an optimal solution, I would say it's a pretty good start to make sure that we're on the right track before we continue with the data migration. And this approach also has its own benefits. For example, it's easy and quick to implement, and it's safer with regards to the data. Because let's say in this case, we've used the branch by abstraction pattern we went over earlier to redirect some of the calls from the monoliths to our authorization microservice. And part of the users were registered during this time. Now, at a later point, if we want to switch back to the old implementation for some reason, there will be no data inconsistency, since all the data have been persisted to the same database. And although this approach looks quite tempting, what we want to achieve as our end goal is something like this. In a perfect world, every microservice has to have its own database and be the only one who is accessing that data. It should expose a well-defined interface through which other microservices can consume that data if needed. This way, we have control over the data and make the decisions on what is shared and what is hidden. We also have visibility on who our consumers at. This way, our microservices are more independent, and this way we prevent use cases where a database schema change has impact over other services who are accessing it directly. Also, hiding the database implementation in the scope of a single service, we have the option to change the database implementation to something that suits our needs better, like, for example, NoSQL database or a key value store without breaking integration in other places. But the main idea is that until we've end up to something that looks like this, our microservice decomposition is not completed, and we can't get the full benefits out of that type of architecture. To wrap up and as final thoughts, I want to say a few words about the things that we went over. Before we decide whether we need to change our architecture, we have to be aware of the real problems we have and we want to solve. Would the new architecture solve our problems, and does the complexity that it brings with it won't make the things worse? Because at the end, everything software engineering is a matter of trade-offs, and we need to be very careful when weighting the pros and cons when making architecture decisions, because such decisions have a big impact over our system, and we have to make sure the price we pay is actually worth it. So that was all for today's presentation. I hope you liked it and was useful to you. And before we jump to the Q&A session, I also want to mention that because of the pandemic situation, we were unable to make this presentation live. So yeah, let's drink a virtual beer together, and we've also prepared some gifts for you. On this slide, there is a link where you can fill up some contact information. So we can send you those gifts.